he's talking about star versions of MN. Okay. And then we will go to the.
Okay, I will make it short. All right, thank you very much. It's a big pleasure to be here. Wonderful. Well, I'm going to talk about the same thing as Boban, about forcing axioms, but kind of in some, I mean, about the classical forcing axioms, not higher forcing axioms. But I also want to, I mean, it's called Martin's maximum, but potentially there is something stronger and it appears very natural. And this is just what I want to talk about. And I should mention in the beginning that my understanding is I have to give 3 talks. So this is my first talk, and then I will give 2 more. And they will all build upon what I'm doing today. And in the end of my talk, I will actually say what I'm going to do in my next 2 talks, in case you're interested. Okay, let's see. So the topic is sort of this, I don't know if we should say tension or relationship between forcing over models of ZFC with large cardinals and forcing over determinacy models, where you make kind of stronger and stronger determinacy hypotheses. It's about, well, forcing axioms, as I said, and maximality principles. Boban already introduced Martin's maximum. I would like to talk about a slight strengthening of Martin's maximum, which is usually called Martin's maximum double plus. And let me write on the statement. So you have a forcing, which is stationary set preserving, and you have a collection. You have a collection of LF1 many dense sets. And also, you're given a collection of LF1 many names for stationary sets. This is what the double plus here refers to. Of names. Is it always like this? I mean,
Yeah, different songs.
Yeah, it sounds kind of sick for stationary sets.
Break.
Yeah, maybe. Subsets of omega 1. Let me just be specific what that means. That means you can say that one of P forces that tau I is a stationary subset of omega 1, then there is a filter G in D such that G meets all the dense sets from D. And the interpretation of tau I by G, which is just the set of all psi, so that, you know, G forces that psi is in tau I. In other words, there is a P in G, so that P forces that psi is in tau I. This is stationary. Okay, that's for all I. All right. Good question.
G is finite?
Finite. Why should it be finite?
Okay. Because
it's a filter in. It's a subset of P, so typically it won't be finite. Otherwise, this. And you have omega 1 many dense sets, so you need them all. Okay. All right. So I would like to. I mean, one of my. I don't like this statement too much, and I think there is a better version. better formulation of that, you can work it, and I would like to give it to you as an exercise. So this statement is equivalent to the following statement, namely that, okay, you start out with the same hypothesis on P, suppose okay, now instead of talking about then sets and names for stationary subsets of omega, you talk about the model. I take an arbitrary model M, whose universe I write as M, and it has a certain signature. It has, let's say, Aleph-1 many relation symbols or functions. So this is at most Aleph-1 relations functions. Okay? And for all sigma 1 formulae, well, in a language where, in the usual language of set theory with epsilon, but you also allow, you augment the language also with the predicate for the non-stationary ideal. So you have a symbol for epsilon, and you have a symbol for the non-stationary ideal omega 1. And in all contexts, you always interpret this symbol as the current version of the non-stationary ideal. Okay. So if in the forcing extension, the sigma 1 statement is true about M, okay, then, well, if I were to write that then V thinks that phi is true of M, that's false, because, for instance, you could have that M, I mean, there is no size restriction on M, so M could be arbitrary of arbitrary height. And so, for instance, omega 2 could be an element of M, and you could say, this is an external statement, this is an external truth. So it could say that what M thinks is omega 2 has cofinality omega 1 or something, and you can do that very easily by a stationary set preserving forcing, right? So I cannot conclude that V thinks. But what I can say is that there is some elementary substructure which I want to collapse. So there is an M bar which embeds into M. So that's an elementary embedding. What's the size of M bar? Well, I don't state it, but typically it will be of size Aleph-1 because you have Aleph-1 many relations and functions there, right? So you can force that this model has a size at least Aleph-1, right? Maybe there are some constants and so on, but typically it has a size equal to Aleph-1. Maybe I should then do these in V, I want to say. Alright, such that the statement so this is my exercise to know that these two things are equivalent, and now I want to move on to a strengthening of that statement by introducing the concept of honest consistency. Okay, there is a definition. Let's formulate in strengthening.
Sorry,
Yeah.
the plus coming here.
Plus is coming in here. So you have a symbol, right? And it's a nice exercise to show that they are equivalent. One direction is pretty easy. So from here to there, that's very easy. The other way around, well, you have this model and you look at the right-hand sets and stuff. Okay. And by the way, it's a generalization of the well-known characterization of bounded forcing axioms, right? So in the case that M has size L of 1 to begin with, typically this will be the identity formulation of. All right. So there is a definition. I want to be in a context where some things are as above. So let's say we have a parameter, or let's say we have a sigma 1 formula in the same language as up there. Okay. And we also have a parameter. All right. So we say that this statement, this is an external statement about the model M. It's not that M thinks something, but it's external, right? It's property about M from outside. And it's honestly consistent. And you relax that you can force that statement right way. So you want to say if, all right, I have to bring in, well, what you basically want to say that, well, it is consistent in a strong way. Okay, so you have to formalize it a little bit careful. You have to say if for all universally bare functions, f, well, what is a universally bare function? If I'm thinking of a function which actually acts on uncountable sets, or potentially acts on uncountable sets. So I start out with a function from the reals to the reals, which is universally bare, and I say that, you know, you introduce the notion of code invariance. So you know, if your real codes a certain element of HC, then you want to say that the image also codes an element of HC, and then you want to say, you know, if two reals code the same thing, then the images under these two reals code the same objects respectively. So that's code invariant. And then when you have a code invariant function and it's actually universally bare and you're in a nice situation, then you can expand in a natural way this function to act on all sets in the universe. Okay, so that's, but let's not go too deep into that for now. For all universally bare functions, there is a transitive model. So where does this model exist? Well, the model exists somewhere. So what you want to do is you collapse, you make, let's say, the transitive closure and accountable. Okay, this is where your model, where you want to look for your model. This is the model of ZB or ZB minus plus phi of A. And okay, this is a sigma 1 statement in this language equipped with a predicate for the non-stationary ideal, and that things kind of work out the right way. You also want to say, well, first of all, I want to say that, you know, let's say the transitive closure of M is contained in A, but I also want to say that if I look at the non-stationary ideal of E, then this is just the restriction of the non-stationary ideal of A to B. Right? So A is something bigger than B. It exists here, but okay. This model certainly collapses omega 1. But still inside here, I could have a model where if I look at its non-stationary allele, it's kind of a conservative extension of the non-stationary allele of the non-Q stationary sets, okay? So a typical example of how to prove that a certain statement is honestly consistent is by forcing the statement. But there are actually other ways to prove that a given statement is honestly consistent. Well, in fact, I don't know.
The phi true of.
I'm sorry?
In the model A?
Yeah.
What is the formula phi true of?
Oh, I see. Sorry. I don't know why I started writing A. This is this model. Sorry.
Okay.
Thank you.
Model is
Yeah, sometimes I write A, sometimes M, and I always get confused. Thank you. Okay, so what did I want to say? So where is it? Here. Okay, so don't worry about this F closure too much. You know what you basically want to say is it's not just a transitive model. Well, it's kind of for instance, it kind of reflects certain large cardinal structure of the universe. In fact, for the formulations of these axioms, you don't need much. All you care about, as far as I can tell, is closure under the M1 sharp operator. So I could as well just say that the model A here is closed under M1 sharp, where M1 sharp is kind of the sharp for the least model with a Boolean kernel. Okay, and now I formulate a principle which is allegedly stronger. I write a star here, and I will tell you in a second why there is a star. And what you want to say is, you forget about forcing. No, here you want to say, if phi of m is honestly consistent, now I say phi of A, and phi of m is honestly consistent, then you have the same conclusion. So it's kind of the same statement, except for that you relax the requirement that you can force this statement somehow, right? Okay. Let's see. And then there are all these other local versions of these axioms. So unfortunately, there is a hierarchy of these axioms, and it's a little bit unfortunate. The whole dry. Okay. Let's see. So you may also say, well, I'm a bit unfair to the people who take notes, but I want to add, you know, I can add a lambda here, all right, which means the model has size lambda. I can also do that with the unstarred version of that. So I can write down the unstarred version right where the hypothesis again is that I can force it. And then what does that correspond to in the old version? Maybe I should. Right. I mean, we had this version, right? Okay. Now I define this principle like here, except for this means that I can force it by stationary set preserving forcing, and then this corresponds to the old formulation of MM double plus, where the individual anti-chains all have size at most lambda. And it's important that you talk about Boolean algebras and not just posets. And sets. I mean, you keep having at most out of 1 million sets, but they individually they have size at most lambda. Oops. Right.
This is a definition of star plus plus. It's not because you still have it written that it's equivalent to.
I'm sorry?
Like if you read the it says star plus plus is equivalent to, but that's the definition, right?
Yeah, it's our definition. I'm sorry. Yeah, that's true. Yeah, thank you. So this is the definition. All right.
And then do we know that this is stronger than NM plus plus?
Very good question. I will tell you everything I know about this question in a second. Okay? Unfortunately, there is even more ugly notation. So if I write this, so this is the set of all universally bare sets. Of reals. And then I can say, now there is an A, or a finite vector of A, so it doesn't really matter. Right, blah, 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 blah. And now I enlarge my language by having a predicate for A here. And also, again, right, I mean, this A is universally bare, so it has a unique interpretation in all set generic extensions. And honest consistency refers to a generic extension where I just collapse everything. So there's always a new version of A, and I want to interpret this A always by the current version of A, right? So it makes perfect sense. Okay. All right.
So is NM star plus plus the same as gamma infinity and star?
Okay, let me tell you, I promised you to tell you everything I know about these things. So these are the definitions. And let's start by some triviality. I mean, for instance, MM, it doesn't matter if there is a star here or not, right? This trivially implies MM plus plus, what people sometimes write off lambda. So that means that's the principle where the, oh, I see, for the start version, this doesn't make any sense, right? Okay, sorry about that. I collapse omega, not omega. I don't, can you ever? Yeah, I collapse everything to omega. But in a model, in an other model where you collapse, make everything countable, you could have this A, which is kind of doesn't, you know, which has this property, right? It's like you do. It's like, you know, you can do a stationary set preserving forcing, and then you just absorb it by a collapse. With this intermediate model, and here it's just something like that. Okay, I didn't write on the definition of this thing. This means this is MM double plus for forcings of size lambda, right? So if your forcing has size lambda, then the anti-chains of the dense sets cannot be bigger than lambda, right? So that's a triviality. I'm not sure what this version would be for a star. Maybe you can cook up some different thing about it. All right. Okay, so as far as, and by way of notation, if lambda is equal to LF1, you don't write it like this, you put a D here for bounded, right? Maybe I should write it here. Okay, so this is equal to gamma. Sorry, one star plus plus, and often often there is no gamma, and it's like this. So you have a whole bunch of, you know, but it's not my fault mostly. I mean, this notation with gamma in front is due to Woodin, and this thing with the plus pluses is due to other people, and yeah, nothing is due to me. Okay. Okay, but the whole thing makes sense because there is a theorem I'm not sure what the optimal hypothesis is. I was thinking of it, but I think you need something like that the non-stationary ideal on omega 1 is saturated. Plus, let's say the universe is closed under the operator which takes an x and maps it to m omega sharp of x. In other words, you have a little bit of large cardinal structure. Both of these things are consequences of MM. So it's kind of a natural context to make these hypotheses. And then the following statements are equivalent. You take as your gamma in this context, every set of reals in L of R is universally bare. So what I want to write here is the power set of R is being computed in L of R, BMM star double plus. It's kind of an awful thing to write, right? But there is something easier, which I don't really want to talk about. So that's equivalent to Woodin's axiom star. If you don't know what this is, take this as the definition. All right. So what does it say? It says, if you trace back, the model would have size L1. So just think of a subset of omega 1. So this is your parameter, right? And what it says that if you have a sigma 1 statement in this language where this is a set of reals from L of R, and if it's honestly consistent, well, then it's true, period. This elementary embedding can be forced to be the identity. So it means that whenever we have a sigma 1 statement about a parameter in H omega 2, which is honestly consistent statement in that language, then it's already true. So it's a kind of maximality principle. Okay, this is this thing. And what I meant to do actually, but there is no time, I guess. I actually wanted to prove this because that's very easy. Yes, that's not hard at all. I can maybe tell you something about the proof. Well, I don't know. I just fear that if I start the proof now, I think I shouldn't start the proof. I mean, for one thing, I would have to explain what star means. And then in the end, it's really the case that the proof is not very hard. So one direction here, namely that if you have star, then you have this principle. I should say this is, morally speaking, this is due to Hugh Woodin, even though he never stated it that way. So there is a proof in his book where he uses star plus the closure of the universe or something to derive bounded Martin's maximum. And that's basically the argument. If you know what star means, you have a certain sigma 1 statement, and you suppose that the negation is forced, and then blah, blah, blah. Okay. So this is due to Hugh Woodin. And the other direction is, you write down a candidate. So star says that there is a Pmax generic filter over L of R, which exists in D, so that in the extension, all the subsets of omega 1 are, all the subsets of omega 1 are contained in the extension by that filter. That's what star says. You write down a candidate for your filter, and then you have to show that it actually meets all the dense sets. But if you fix a dense set from L of R, well, one of these guys, and the statement that there is a condition in your filter which meets the dense sets is exactly of that form. And you can write it down in this fashion. And it's pretty easy to show that it's honestly consistent. And that's an argument which doesn't use any forcing. There is no forcing there. So fixing a dense set in Pmax the statement that there is a condition in that dense set which is in your candidate filter, which you write down. This is exactly of this form, and you can show by some argument which doesn't involve any forcing that it's honestly consistent, and therefore it's true, and then you have this. Right? So this direction from here to here is also easy. Okay, and if you're interested, this stuff is in an old paper of mine with David Aspro like 10 years ago or even more. Okay, but a little bit more surprising is that you can drop the star here. Okay, so I said that you wouldn't actually basically prove that you can go from here to here. 1 implies 3 is entirely trivial. And to go from here to here, well, this is this theorem of mine with David Aspro where we show usually it's stated in a way that you say that MM double plus implies star, but if you look at the proof, that's exactly what we need to get this consequence. So what you have to do is you do exactly what I said before. You have this candidate filter. You give me a dense set in L of R, and I have to show that there is a condition which is in that candidate filter and is also in that dense set. And it's very easy to see that the corresponding statement is honestly consistent. And then from there, I have to show from honest consistency, I have to cook up a forcing which actually forces the same thing. And that's possible. And this is done in the proof. Okay. All right, so that's what I know about the relationship of the bounded versions, the star and the unstarred version. So they are more or less the same, and you can also, you can vary here, right? I mean, it's actually you can write here whatever you want, and then the course or just nothing, the empty set, and then these two versions are equivalent. All right. Okay, under the right background hypotheses. Okay. What I don't know is if you, for instance, cross that out, if you want an open problem, is there a reformulation of BMM itself, where there is no, or BMM double plus, let's say, where there is no mention of sets of reals in L of R as a star-like axiom, right? And star-like means in this fashion, so there is a filter over for Pmax, maybe which is not dense for which is not generic over L of R, maybe it's kind of only partially generic. We worked on this a little bit, but I don't see it. But there should be something. You should meet, this filter should only meet certain sets, sigma 1, 2, or sigma 1, 3 sets or something. It's somewhere there in between, and we couldn't really figure out. That's an open problem. The other open problem is, and now I come to your question. So this is basically for lambda equals L1, and above that, strictly above that, I don't have the faintest idea. So is well, I should be a little bit careful. For lambda, at least LF2 is, well, all these variants. Let me just write gamma mm plus lambda equivalent with gamma mm bar double plus lambda. Or you could just say is no, a clearer version would be is MM star double plus equivalent. Double plus. I would say, in the light of that theorem which I wrote on there, it would be very natural to suspect that the answer is yes, but I don't have the faintest idea. And the proof we have for the equivalences there explicitly don't give that result, so there is a problem. What I also don't have, and I thought about it, but I just couldn't come up with something, I don't have the kind of a test question. I would like to have some statement which is implied by this and is not known to be implied by that, and I couldn't cook up anything, but I didn't try too hard. So there isn't really a test question. I'm sorry. Yeah, this is my next question. Where should I put that? Maybe here. So 10 years ago, I wrote a paper on MM star double plus, and I was very surprised that the referee didn't ask, do you know whether it's consistent? Because it's not even asked in the paper. I just stated the thing and nobody. So I'm very glad that you asked. So that's also open. Okay, let me state it like this for lambda above L3 is m, well, whatever, gamma doesn't matter here. I don't even know mm lambda star plus consistent from large cardinals. I'm, as I mentioned, I'm not able to show that MM star double plus holds true in the canonical model kind of for MM or MM double plus. I don't know what the answer there is. Okay, so there is an LF3 here. Let me just see. So it is, okay. So why is there an L3 here? So what I want to do is, I want to do two things. So in my next two talks, what I want to do is I want to address the following two questions. I mean, first I would like to where is it? I just erased it, right? I mean, there was this equivalence of bounded Martin's maximum star double plus with maximum bounded Martin's maximum double plus, and it goes. You often make it go through a star, but this is completely irrelevant. So there is a direct proof. If you do it like this. If you know something about Pmax and star, so star has this feature which is called pi2 maximality. So from star it follows, star and some large cardinals, it follows that if you have an omega consistent pi2 over h omega 2 statement, then it's actually true. Okay. Pi2 h omega 2 maximality is the statement. If you have a statement phi, now there are no parameters, and it's pi2 over h omega 2. In the usual language of set theory, now there is no predicate for the non-stationary ideal or something, and no predicates for universally bare sets. And omega consistent. What is omega consistent? Omega consistent is something like honestly consistent. I mean, it's older than omega consistent. it was introduced by Hugh Wooding, you sort of do the same thing. So there is no parameter here, and then omega consistent is kind of the same thing. You say that for every universally bare function f, there is an f-closed transitive model. Well, typically the model will be countable, so you don't have to do any collapse if it exists in some collapse extension already exists in B. And it's a model of period. Nothing like this here. Okay? So this is omega consistency. So you say that if a statement, if a pi2 statement is omega consistent, then phi is true. And you can use this machinery which got developed along the lines of proving the equivalence of BMM star plus plus with BMM plus plus. The key thing there being that if a statement is honestly consistent, then you can force it by a stationary set preserving forcing. So this can be used in a direct proof of that thing, and I kind of like it. So one thing I did not mention, but I should have mentioned, is that that actually in many cases here, it doesn't make the principle stronger if you write a gamma here. For instance, the unbounded MM, let's say double plus, just implies the gamma version. Because, you know, you have your gamma here, you can always throw them into your model. If there is no size limitation on the model. I should have mentioned that, but don't worry. Okay, in any event, I mean, if you don't really want to think about what exactly do I need to prove it, there is a nice direct argument from here to prove this sort of pi2 maximality. Usually you go to star, but you don't have to do that. You don't have to know at all what star is in order to do that. So this is one thing I thought I could do. And then another thing is, so the consistency of a very bounded version of Martin's maximum star, namely MM star. The focus here is on this star, and there is an LF2 here, but I could also write 2 to the LF0 here, and then it will actually imply that the continuum, that this guy is LF2. Okay, by forcing over a model determine this, yeah, I don't know. Let's write D for that model. So is a model of determinism. So D is a model of something like, I mean, one feature is AD, but you don't really care about AD. You only care about consequences of AD, which turn out to be equivalent to AD, but never mind. And theta is a regular limit of the Solovay sequence, which is kind of the same as saying that every set is Suslin, but you want a stronger this is kind of redundant by what I'm saying next, namely that every set of reals is universally there. So these hypotheses are consistent, and then you force by, so if you start out with this model, then the Pmax extension of P, you start with this model, you do Pmax, you don't get a well order of this, you do get a well order of the reals, but not the set of reals. So you do that by, I don't know, some people write add, and I always write call omega 3, so you collapse omega 3 to omega 3, right? You add a current subset of omega 3. That's a model of TFT plus this principle. And I would like to sketch a proof of that. And why do I find this interesting? Well, I find this interesting because this is just, I mean, I would find even more interesting if I had, you know, like test questions here. If I could give you a statement which follows from the star version, but it doesn't, I don't see why it follows from the unstarred version. I don't have such a thing. Maybe one can think about it. But also, it's interesting because, you know, you want to check out. One say MM is the strongest principle. Yeah, sure, in some sense it is. You cannot enlarge the class of forcings, but you can make it stronger by putting a star here. It's allegedly stronger, and you just want to see how far you can go into that direction, or maybe it becomes inconsistent for some mysterious reasons. So it's not known how to get that. Over a CFC model. Of course, we will need some large cardinals, I guess. All right. Wait a second. I was a bit fast. Well, is it okay my stuff, or
Yeah, it's okay.
yeah? I mean, this is a, you know, this is what I had to say. I mean, I was planning to sketch the argument of this, the proof of this thing, but I think it would have taken too much time. So this is my plan for the next two talks. Thank you very much.
Because Ralf was waiting.
He was first, I think, but I'm not sure.
I
Right. Maybe you were first. I don't know.
So my question is that do you get, like in this case, when you force over this determinism, do you abstractly get a different variant of star? Like,
What does it do?
so star is like there's a generic over L of R, such that you get all subsets of omega 1.
I mean, in that model you do have star because.
But is there like an abstract like a strengthening of it so that it becomes equivalent to MM star plus?
I see what you mean. Oh, that would have been another. Yeah, that's a very good question. I could have also stated that, right? I mean, I went kind of downward by saying, what about just BMM without universally without sets of reals in L of R, and what kind of version of star is it equivalent to? So I went kind of down, but you can also go up and ask, well, I don't know. Maybe in the end there is something, right? I mean, maybe there is a star reformulation of Martin's maximum. I don't know. Mhm.
And it's a kind of very straightforward question. So do you expect the start version of MM++ to be actually stronger consistency-wise from MM++, or does it some consequences you expect MM++ not to have, or
Yeah, unfortunately, at this point, I don't really have any conjecture.
what was the plan, right?
So, yeah, because I don't really see how you would force it. I don't. There's a technical problem. I mean, there is an obvious approach, and it kind of doesn't work.
What is the obvious approach?
You run this argument I have with. I mean,
Obvious approach.
what the proof I have with W, what does it really do? It shows that if you have an honest, consistent sigma 1 statement about a parameter which is in H omega 2, then you can force it by a station. So why does the parameter have to be in H omega 2? Why can't it be bigger? Well, the argument doesn't work. But it's kind of technical. If you look at the argument, it falls apart. What you actually need is, abstractly, what you need is the following, that your honest, consistent statement is simultaneously honest, consistent with the statement that the cofinality of omega 2 of V is equal to omega. Which is very easy to arrange. If your parameter is just a subset of omega 1, but if the parameter is bigger, then your statement could say that the cofinality of omega 2 is omega 1. This is not compatible with being equal to omega, because then you collapse everything to omega. And without that, it just doesn't work. So, that's another way to look at this kind of set of questions. I mean, from a technical point of view, I could tell you something about it. It will come up in this context, actually, with here. This is something I will talk about. If you have a model, if in B the non-stationary ideal is saturated, and then in some other model that you have where you don't kill stationary sets, but you have that the cofinality of omega 2 is omega, then H omega 2 of V is an iteral of a countable structure, a generic iteral of a countable structure. That's heavily used. Right.
Okay, so let's think of for someone.